Advanced ceramic nanocomposites. Section 3. Consolidation and grain growth of nanocrystalline ceramic powders. Previously, in the course Advanced Powder Technologies, modern technologies of sintering of powders materials were considered. Such technologies like spark plasma sintering, microwave sintering, and rate control sintering are suitable for obtaining nanocomposites. In this lecture, we will consider several modern directions of obtaining dense ceramic nanocomposites. To fully exploit the distinctive properties of bulk nanocrystalline materials, nanometer-scale powders must undergo densification to attain specific properties, geometry, and size in their final parts. The critical aspect of nanopowder consolidation lies in achieving densification while minimizing microstructural coarsening and undesirable transformation. Notably, controlling grain growth during intermediate and final sintering stage as well as preventing ostward ripening is essential. Also, the densification process for conventional powders is well documented. Consolidating nanopowders presents significant additional challenges from both theoretical and practical aspects. Primarily, the substantial surface area of nanoparticles lead to a widespread agglomeration, negatively impacting the densification process. Moreover, an ongoing question pertains to whether sintering mechanisms remain consistent across grain sizes and if they undergo changes at nanoscale level. Several reviews have addressed to nanopowder processing and specific nanosintering issues, highlighting the complexity and ongoing research in this field. Now I select the few sintering technologies I try to combine it and which are suitable for consolidation of ceramic nanocomposites. The first one is pressureless sintering. The next is pulse plasma sintering and hot pressing. The next one is modern technology which quickly developed is microwave sintering. The sintering with applied pressure is the sinter forging, hot isostatic present, and quite novel technology, so-called cold sintering. All of this technology of nanocomposites, ceramic nanocomposites sintering will be observed in this lecture. Nanopowders are highly unstable by a thermodynamic point of view. The tendency to reduce the extensively large surface area per unit volume of the nanocrystalline powder is the mechanism that drives the sintering process. The extra energy of a surface with a radius of curvature R may be calculated as a stress as given by a Laplace equation. In nanomaterials, this sintering stress may reach very high values. For instance, the sintering stress may be as large as 300 megapascals for 10 nanometer particles, compared to only 3 megapascals for 1 micron particles in diameter. From the kinetic point of view, we expect enhanced densification for processes that display a direct grain size dependence. For sintering, this dependency may be illustrated using the equation for the densification rate developed by Johnson and colleagues and used for all stages of sintering. The nanocomposite approach to engineering ceramic microstructures has received much attention in the ceramic literature. This research area was initiated by Neha, who reported large improvements in the mechanical properties when a ceramic material has reinforced with nanometer-sized particles. There has, however, been a wide spread in the result presented by different researchers because of difference in fabrication and testing procedures, and some of the improvements have not been produced. The production of a fully dense material with a homogeneous dispersion of the reinforcement agent is a key factor in the fabrication of ceramic nanocomposites. A porous microstructure and agglomerated second-phase particles would degrade the performance of the composite material. It is well established that inclusion of second-phase particles may suppress grain growth, but the particles will also obstruct densification. For pressureless sintering, the presence of large interagglomerate pores in the nanoceramic powder compact is shown to be a root cause of high sintering temperature and slow densification rate. The strong dependence of densification rate on pore size with a smaller pores yielding faster densification rates and higher densities at a given grain size can be achieved. In contrast, variation of ceramic sintering schedules are generally unproductive or counterproductive with respect to altering the density grain size trajectory. For example, Meyer in her investigation tested two consolidation methods which help successfully produce fully dense nanocrystalline ceramic. Include dry pressing at high pressure around 1 GPa prior to pressureless sintering, and sinter forging. Both approaches greatly reduce or eliminate the large pores present in a starting compact. Wet processing techniques have not yet widely used for nanoparticles. Also show promise in this regard due to the minimal force required to obtain efficient particle packing. Nanocrystalline ceramic made by preliminary by the compaction and sintering of ultrafine particles. A brief look at the theoretical literature on the sintering ultrafine powders tends to be very encouraging. Rules to thumb such as Herring-Scullin law would predict that nanoparticles should sinter it easily at low temperatures. For instance, in comparing two powders with grain of crystallite size J1 and J2, Herring-Scullin law predicts that sintering temperature will be lowered from temperature 2 to temperature 1, according to present relation. In the above expression, n is the grain size exponent, typically 3 for densification mechanism in surface diffusion, 4 if the densification mechanism is grain boundary diffusion. R is gas constant, P is the relative density, and T is time. In practice, such easily sintering of nanoceramic powders is rarely achieved. More commonly, the nanocrystalline powder begins to sinter at quite low temperatures, but fully density is not reached until much higher temperature or longer times. This with the result that the grains grows well beyond their intended nanometric size. As an example, you could observe the microstructure of sintered nanocrystalline titania powder with a starting grain size of 10 nanometers and green density around 46% of theoretical. Here you can see a big intergranulate pores. An agglomerate can be defined as a bonded mass of group particles, and agglomerated powder contains many such masses. When an agglomerated powder is compacted, the hard agglomerates pack together as rigid and tight, leaving behind pores on the scale of the agglomerate size. If the agglomerate are micron-sized, one obtains a very large pores, micron-sized pores of that. It leads to a requirement for high sintering temperature. To avoid problem with the uncontrolled grain growth at high temperature and high percentage of residual porosity, the composition of ceramic material and modern sintering technology must be applied. For example, Gustafsson and colleagues investigate fabrication process of high-density pressureless sintered aluminum oxide with 5-volumetric % silicon carbide nanocomposites without special additives. As authors showed, the silicon carbide particles were well dispersed in the microstructure and located predominantly on the interiors of aluminum oxide matrix grains. Pinning of grain boundaries of second phase in matrix material for nanocomposites could essentially suppress the grain growth. These effects could be used for microstructure engineering of composite material. The work of many researchers has shown that samples that don't respond well to pressureless sintering even after compaction at high pressures can sometimes be made successfully by sinterforging. Sinterforging is an operation in which the sample is compressed at elevated temperatures such that it deforms and densifies simultaneously. It differs from hot pressing in that a die is not used, so that there is a high ratio of divarotic, also called shear, to hydrostatic stress. There appear to be at least two densification mechanisms which operate during sinterforging. The first, stress-assisted diffusion. It's similar to the diffusional densification mechanism in pressureless sintering. The difference is that the applied compressive stress lowers the vacancy concentration at grain boundaries, so that the vacancies now move more quickly from the pores to the grain boundaries in accordance to the fixed first law. A faster pore shrinkage rate and hence a faster densification rate results. Theoretically, there is no limit to how large a pore can be closed by a plastic flow. However, it should to be noted that a significant amount of plasticity is required. Strains around 0.62 by one theoretical calculation, but more is often needed in practice. Hence, only those ceramics which are superplastic, it is capable for deforming to true strains of 100% or greater, are able to take advantage of this mechanism. Despite the advantage of being able to readily close large intergranulate pores, sinterforging doesn't offer some disadvantages. A significant one is the fact that the applied strain causes to an additional type of grain growth, termed dynamic grain growth. In dynamic grain growth, the grains enlarge in direct population to the amount of applied strain. Thus, the very large strains needed to close pores also induce a correspondingly large degree of grain growth. A final difficulty with the sinter forging is that die friction effects can prevent plastic strain, and hence densification, from being evenly distributed with the sample. On the present schema shows that complex stress state which exists and uniaxiality deformed sample when the die friction is significant. The nearly hydrostatic stress rate in the region 1 cannot give rise to microscopic plastic strain. This requires shear stress, which are dominant in region 2. Not surprisingly, the sinter forged material in region 2 is denser than that in region 1. Region 3 suffers from significant tensile hoop stress, which not only discourages the closure of pore but also causes cracks to form on the outer surface of sample. The second mechanism of densification due to sinter forging is the closure pores by plastic flow of surrounding matrix. In this mechanism, matrix material is physically pushed into the pores to fill them, as the bulk material is deformed. By virtue to plastic deformation, a property unique to fine-grained ceramics. It is possible to close pores which are much larger than those that can be closed by diffusion. As an example, the sample with many large pores which was presented on previous slide for titanium dioxide would be fully densified at the same temperature during 45 minutes at the temperature around 600 centigrade using the sinter forging technique. During the last few decades, high-speed working of materials has occupied an important position in industry, as it had been used successfully in producing engineering components at competitive rates. The deformation pattern during high-speed sinter forging process is influenced by several factors, which interact with each other in a complex manner. The decisive factors are the density of the preform forging temperature, lubrication condition at the die workpiece interface is low stress of the sintered materials, and the factors related to a forging equipment such as deformation speed and contact time under load. Many solutions of sinter forging problems have been reported on the various technological aspects of industrial processing of sintered material. In high-speed sinter forging process, the surface of the workpiece is distorted and takes on an impression of die surface. Therefore, the actual contact area, as far as the specific cohesion of surface is concerned, is not negligible. Friction conditions in forging are essentially different from the sliding friction in machine parts. The relative velocity have been the workpiece material and the forging die surface together with a high interfacial pressure and or deformation models will create the condition essential for adhesion in addition to sliding. The change in relative density depends upon the processing conditions such as speed and surface condition. During the high-speed sinter forging process, the compressive force supported by impact gradually increases the relative density to hence the real area of contact grows and approaches the apparent one of the force area. The novel modification of the method is electrically sinter forging. Electrosinter forging is an industrial single electromagnetic pulse sintering technique to rapidly produce a wide range of small components of metal, alloys, intermetallics, and ceramic and nanocomposites, including ceramic. Electrosinter forging can be described as the superposition of a single mechanical pulse with a single electromagnetic pulse that generates a direct electric current through the powders previously loaded inside an insulating die. As long as we have the superposition of the two pulses, no matter how long these pulses are, we are in the domain of electric sinter forging. If not, we cannot really talk about electrosinter forging, but more about resistance sintering. The effect of this superposition when acting on metal or composites powders can be near fully to full consolidation. Even when the two synchronized processes last as in all the results described only 20-30 milliseconds. The method is carried out in air as no advantage has been observed thus far using the vacuum or argon as a protective media during consolidation. A typically present-day capacitor discharge-based machine will produce peak voltage on the plunge between 40 and 60 volt and peak currents from 800 kiloamperes to 1.5 milliamperes, with energies stored on the capacitor from 30 to 120 kilojoule. The axes are powered by electrical linear actuators for versatility, speed, and reactivity. The current machine has a peak force of 120 kilonewtons, while a newest one currently under design will be 240 kilonewton or above. For example, applying these methods possible to create metal matrix composite with high volume percentage of ceramic phase, for example, titanium carbide. Sinter forging is a combined superplastic deformation and sintering process. The technique is developed and mainly used for ductile materials such as metals. Since nanoceramic exhibit superplasticity at high temperatures, sinter forging has been applied for nanoceramics too. For example, it's possible to make deformation of nanocomposites in spark plasma sintering equipment. The deformation test could be applied for electric sintering. For example, a superplastic deformation of press-sintered silicon nitride-based nanocrystalline ceramics, it's silicon nitride with titanium nitride, pure silicon nitride, and silicon nitride enhanced by nanoviscers of silicon nitride, where could be deformed in electric sintering equipment. Superplastic deformation tests in this case were carried out at the temperature from 1500 centigrades to 1600 centigrades. at high deformation rates were achieved. The composite is enhanced by silicon nitride nanowhisker exhibit the formation of anisotropic macrostructure with the same measured anisotropic mechanical and tribological properties. Superplastically deformed titanium nitride with silicon nitride composites exhibit fine-grained microstructure with an average particle size around 30 to 150 nanometer. The present study indicated a possibility to use superplastic deformation for production of complex shape materials based on nanocrystalline ceramics, nanoceramics, and materials with textured microstructure and unusual properties like tribological and mechanical properties. The next technique is hot isostatic pressing. This technique uses flexible dies and hydrostatic pressure for densification, with the understanding that hot isostatic pressing was developed and has been mainly used for hard-to-sinter ceramics. It is still reasonable to say that its application to conventional sinterable but nanosite ceramic is not as common as it should be. Contrary to the substantial hardness encountered in nanoceramic densification. Overall, hot isostatic pressing is not as widely applied to oxide ceramic as it can be potentially to be, and this trend shows no indication to change. For non-oxide ceramics, hot isostatic pressing has been applied to both carbide nitride ceramic as well as their composites. The relatively more active research activities for these materials are likely facilitated by the knowledge accumulated from the micron-sized carbides and nitride ceramics. For example, it's possible using hot isostatic pressing when the pressure applied from all sides of the sample authors showed, Liu and colleagues showed that nanostructured silicon carbide could be successfully densified by HIP process. Dense and homogeneous nanostructure with grain size around 100 nanometer was obtained at the temperature around 1850 centigrade and pressure around 200 MPa after sintering for 1 hour 54 minutes. The glassy silicon oxide layer on the silicon carbide grains plays an important role in obtaining the nanostructured, as was shown by authors, that this layer helps to fully densify the material using hot isostatic pressing, especially at very high temperatures. In recent years, Chen and Wang has developed an effective method for sintering of ceramic materials. They start from sintering of yttrium oxide and call this technique two-step sintering. Designed to heat the samples to a high temperature, temperature 1, and rapid cool down to a lower temperature, temperature 2, for a long period. By this method, the grain boundary diffusion of the specialty is maintained, but the grain boundary migration could be frozen under pressureless sintering, conditions of sintering. Therefore, the grain growth of the final at the final sintering stage is suppressed successfully, and they showed this effect for yttrium oxide ceramics and it's possible to obtain materials with nano-sized grains. This method has been also applied for various materials such as barium titanate, zinc oxide, aluminum oxide, silicon carbide. According to the reported works, the attention has been focused on a choice of the sintering temperature, so-called temperature 1 and temperature 2. Temperature 1 and temperature 2, when we decrease the temperature from temperature 1 to temperature 2, and investigate the grain growth behavior during the second step of sintering. Two-step sintering consists of heating the sample in two stages, as we can see. Different sintering profiles were applied in two-step sintering. Generalized diagrams you can see here. It's common two diagrams of two-step sintering techniques. As shown, the microstructure of fine zirconia grains in two-step sintering sample induce a pinning effect in grain boundary migration of alumina. Thus, the degree of grain growth during the second step sintering is effectively reduced as comparing with ultra-pure alumina powder. High ceramic density is over 99% with small alumina size controlled of submicron level is achieved by authors after applying two-step sintering. Two-step sintering with a high first-step sintering temperature is widely used to obtain fully dense ceramic with controlled grain growth due to lower second-step sintering temperature. The mechanism for controlled grain growth in two-step sintering with high first-step sintering temperature was firstly proposed, as we mentioned, by Chen and Van. For two-step sintering study on yttrium oxide, and it's widely accepted for verified for other ceramic. In general, mechanisms that are responsible for densification during sintering are grain boundary migration and grain boundary diffusion. Grain boundary migration is responsible for the rapid grain growth in the final stage of conventional sintering. This densification of ceramic with grain growth suppression at the second step sintering can be explained by the absence of grain boundary migration during the second step sintering as described previously. As was discussed previously, in conventional single-step sintering, the grain growth is accelerated due to grain boundary migration and grain boundary diffusion in the final stage of sintering. Rapid cooling before the second stage of sintering freezes the microstructure by immobilizing the triple point junction, and continuous densification will be achieved by grain boundary diffusion. For a successful two-step sintering profile with higher first-step sintering temperature, few conditions should be achieved. At the end of first-step sintering, the sample must be reaching a critical density. At the end of the first step sintering, so that the densification is active in the final sintering step. This critical density depends on the material. Important study on exploring the mechanism of grain growth suppression of two-step sintering with the higher first-step sintering temperature was reported on zinc oxide ceramics. The transmission electron microscopy images of two-step sintering samples at the first step sintering temperature around 800 centigrade for 60 seconds and the second step sintering temperature 750 centigrade for 20 hours. It could be seen on a picture. And the conventionally sintered zinc oxide at temperature 1100 centigrades were examined as for evidence of grain boundary migration. 10 different grain boundary zones were analyzed by investigators using TEM images. And as they report, they seen in junction seems to have pinned the boundaries on growing grains, and the curvature of these boundaries resulted from the mentioned immobilized triple point. However, no similar zones are observed in the TEM images from conventionally sintered samples. One contemporary trend is unconventional sintering techniques, and connected to these unconventional sintering techniques, we just discussed it's two-step sintering, and the other is so-called rate control sintering. We discussed this technique in my previous lectures, and now we show how to apply this technique for nanoceramic materials. This method of non-isothermal, non-linear sintering schedule has attracted the attention of ceramics due to its wide possibility for structural control. Specimens sintered under rate control sintering conditions are characterized by fine grain size and pore-free structure. Such results were attained by established feedback between the sintering temperature and the instantaneous density. With the goal of densification rate control at each stage of the sintering process, authors which work with rate control sintering concept proposed the heuristic idea that is the maximum safe rate of shrinkage for each level of fractional density. This restriction of shrinkage rate is necessary to control both pore and grain structure evolution. It means that it has to be reach the specific densification rate. To date, the methodology of rate control sintering has been mainly applied to ceramic materials, but for metallic powders the number of investigations is negligible. However, the controlled sintering of carbonyl iron powder displayed that it's possible to apply not only for ceramic materials but for metallic materials too. The rate control sintering technique was used as a structural-oriented type of sintering that substantially limits the grain growth compared to conventional pressureless sintering, and produced dense ceramic with high hardness, fracture toughness, and stress. It was reported, but a lot of investigators. The main advantages of the rate control technique over conventional pressureless sintering is that it is possible to achieve final density around 99 of theoretical, keeping the grain growth, the grains less than 100 nanometers from starting nanometer powder. The rate control sintering technique described in different papers where the multi-stage rate density profile depending on nature of the material and the powder particle size is considered to be unique. The basic task of rate control sintering is to determine the maximal densification rate and thus to select the optimal sintering mode by analyzing dilatometric tests on sintering with constant heating rate. The authors who work with nanopowders, for example, with titanium nitrate nanopowder, starting powder with particle size around 50 nanometers, applying rate control sintering, report that at a quite low temperature, around 1300 centigrade, 1200 centigrade, the grain growth could be suppressed and the nanograin ceramics could be obtained. Rate control sintering enables control of microstructure evolution during sintering because of a feedback existing between densification and heating rate. The first stage of heating during rate control sintering follows the methodology of rapid rate sintering. It is well known that open porosity effectively impedes the grain boundary migration. During the final stage of sintering, around 90% of theoretical density, here you can see, the open porosity network loses stability, forming closed spherical and ellipsoidal pores, which are located in triple junction. Splitting of cylindric-shaped pores and localization of spherical pores are accompanied by extending grain growth. Flexible control of densification during rate control sintering maintains an open network of pores at higher densities, 92-96% of theoretical, than in conventional sintering, resulting to a finer grain microstructure. For composite two-step sintering, which was proposed by Chen and Wang, exploits the competition between the driving force of grain boundary control densification and grain boundary controlled grain growth to achieve densification without grain growth during the final stage of sintering. This problem is identical to the one of the final stage of rate control sintering. The success of two-step sintering is determined by the pore morphology of the material prior to low-temperature second-stage sintering. Initially, the authors of this method proposed using rapid rate sintering to obtain a high starting density above 70%, at which all pores become subcritical and unstable against shrinkage. However, as previously mentioned, rapid rate sintering is not always an optimal technique for production of a narrow uniform pore size distribution within a material, which is necessary condition for successful two-step sintering. The goal of the first step of two-step sintering is to produce a uniform pore microstructure with minimizing grain growth. Therefore, the sintering protocol for nanocrystalline ceramics should utilize the advantages of each aforementioned technique. The proposed combined sintering method, rapid rate sintering, rate control sintering, and two-step sintering, and atmosphere controlled for this during the consolidation process. Combining a controlled atmosphere with a flexible sintering profile effectively suppressed grain growth, for example, as shown also for barium titanate ceramic materials. And it's possible to produce fully dense nanocrystalline ceramic with an average grain size of around 100 nanometers. Modified rate control sintering modes were successfully used for consolidate nanostructural composites that based on refractory nitrides. To produce materials with a volume more than few cubic centimeters, a general process of sintering composites in hydrogen in nitrogen was developed based on dialitometric experiments on sintering of titanium nitride with composite pure titanium nitride and titanium nitride in composites with nano aluminum nitride and silicon nitride. Spark plasma sintering is traditionally is a novel technique which useful for consolidation of nanopowders, especially ceramic nanopowders, especially high melting point ceramic nanopowders. Spark plasma sintering is traditionally organized as follows: fast heating rate at around 100-200 centigrades per minute at a pressure up to 200 MPa, followed by holding for several minutes at high temperatures. Using such mode to consolidate various ceramics allows achieve a density around 97% at the temperature lower during on the temperatures on about 100-300 centigrade lower than during hot pressing or pressureless sintering. In such conditions, however, grains grow rapidly, even if the initial nanopowders used for example, if we use nanopowder with particle size around 30 to 70 nanometers, using traditional schedules of spark plasma sintering, resulting in coarsening structure up to submicron structure we obtain, material with submicron structure we obtain. A new approach of the spark plasma sintering consolidation of nanopowders, especially for refractory compounds, based on conception of controlled processes, was proposed by authors. Controlling the shrinkage rate in spark plasma sintering made it possible to develop and test a multi-stage non-linear schedule. For sintering of nanopowders of in different composition. Formally, spark plasma sintering and hot pressing are comparable processes whose kinetics can simplify describing by the next equation. This equation declares that the densification rate is a function of pressure and temperature. Nonlinear spark plasma sintering involves several stages. For example, here presented 3 stages. The first stage with a high heating rate and lasting until reaching a density around 75%. Intermediate stage with a high heating rate. Intermediate stage with a reduced heating rate, and the final stage with minimum allowed heating rate. Relatively low pressure, sufficient to ensure good electrical contact, is applied to the powder material at the beginning of the process. During consolidation, the pressure steadily, smoothly increased, and it's controlled at the points of changing the heating rate, which allows maintaining high densification rate and achieving high density of the sintered material. As example present here, you can see the model of sintering for titanium carbonitride nano powder. The densification of the material during nonlinear spark plasma sintering is mainly stimulated by the rearrangement of particles in the early stage and is a diffusional controlled process in the final stage. The pressure increase and simultaneously reduction of heating rate in nonlinear spark plasma sintering prolongs the rearrangement of particles when grain growth is minimal, which makes it possible to form a homogeneous fine-grained structure of the material. At the same time, reducing the heating rate at the final stage allows avoid holding at high temperatures and obtain a nanomaterial with a density close to the theoretical density. Nonlinear spark plasma sintering can successfully applied to consolidate refractory nanocomposites. For example, nonlinear spark plasma sintering was used to consolidate composites based on nanopowders of titanium nitride, titanium nitride with titanium dibride, titanium carbonitride in composition with silicon nitride, with silicon nitride nanofibers. Here you can see the microstructures of densified materials. You can estimate the grain size of these materials. It's real nanoceramic materials could be produced and near fully dense materials. Currently, innovative sintering methods are being explored and studied in order to modify densification mechanisms that may improve the microstructure and mechanical properties of sintered material, and also is very important to reduce time fabrication of these materials. It's microwave sintering. Two-way stations have been recognized during the sintering process, densification and grain growth. The main purpose of modifying sintering mechanism is to obtain relative density close to theoretical values, very mainly controlled but limited grain growth. Also, the optimization of the process by reducing heating rates, improving aspect of being considered. As a consequence, the novel non-conventional method have been now investigated and developed. Particularly, microwave sintering represents an interesting opportunity at consolidating advanced ceramic materials with a reduced processing time and energy consumption by utilizing electromagnetic radiation to provide high enough temperatures that allow full desiccation of material. The most important advantages of microwave sintering against conventional sintering methods are listed as follows: shorter sintering time and lower energy consumption. Higher heating rates can be used. Material with a fine nanometric microstructure with a high degree of densification and enhanced mechanical properties may be obtained due to the densification mechanism involved. Flexible due to the possibility of processing near net-shaped materials. Microwaves have been used since 1960s for heating purposes, particularly for food and water-based products. Industrially, the use of microwave energy has become increasingly important because it represents an alternative and traditional with a high-temperature process. For example, so far it has been employed in wood dyeing, resin curing, and polymer synthesis. The growing interest in industrial microwave heating is due to mostly to the reduction of production costs, resulting from lower energy consumption and shorter processing times. However, several aspects need to still be investigated, as each material behaves differently in the presence of microwaves. The application of microwave heating has now expanded to material science and technology, beginning with process control and moving on to ceramic drying, powder calcination, and decomposition of gases, with microwave plasma in addition to powder synthesis. Scientific interest on this powerful tool has been recorded in the study, as there has been an increase of bibliographical entities for the term microwaves. In the last decades, because the application of this technology have diversified enormously. In the last 25 years, research have developed on this dielectric heating attributed to microwave began with topics in chemical synthesis and material processing, such as reactive sintering of superconductors, magnetoresistor, nanomaterials production, vitreous phase formation, hydrothermal generation of zeolites, among others. In this sense, one of the major areas for the research and development of microwave heating involves sintering of ceramic powders. In a general sense, microwave sintering increases the densification of the material at lower dwell temperature when compared to conventional sintering, employing shorter times and less energy, and resulting in improvement of microstructure and mechanical properties. Here you can see the microwave furnace which operate on air up to the high temperatures. It could be treat different materials up to the temperature 1200 Celsius grade. And here you can see the quite speed heating rate during microwave sintering. This is schedules of microwave sintering. Microwave heating is a non-conventional sintering technique to solve the difficulties found in previous techniques such as spark plasma sintering. The microwave technology was specifically designed to fabricate ceramic bodies with a high density, very low secondary phase proportional, and high mechanical properties. An important characteristic associated to microwave process, it is possible to directly obtain material with a complex part, near net-shaped components, directly in the microwave furnace without the application of pressure and without any carbon contaminator. This proposes other significant advantage compared with the spark plasma sintering. This point is essential in order to use this sintering technology, where the final dimension of a sintering component has to be almost constant in order to reduce the final machining cost of nanocomposite. Here you can see how to be sintered to a near fully dense density. Nanocomposites from silicon nitride with titanium nitride. It had to be mentioned that these two ways have a different absorption of electromagnetic energy of microwave diapason, and this material, when we combine this material in composition, we have to select the optimal composition for sintering of bulk material to densify it homogeneously and to save the nanostructure in this ceramic to achieve a high mechanical and tribological or other properties. And finally, I will show you the novel technique called sintering. Cold sintering process is a non-conventional, low-energy sintering technique that promotes the densification of ceramic in the presence of transient liquids under low temperature, around below 300 centigrades, and pressure below 500 MPa, megapascal. Since its first introduction in 216, cold sintering process has gained worldwide interest from the scientific community. A green and innovative fabrication route due to the dramatic reduction of processing time, energy, and cost. Cold sintering resembles the geological formation of rocks, where a ceramic powder is densified with the aid of a liquid phase under an intense external pressure and limited heating condition below 350 centigrades. Up to date, tens of different materials, including composites, have been successfully processed using this method. Processing features and variabilities, possible densification mechanism, and issues also for the realization of ceramic-based nanocomposites take place. Advantages with respect to existing techniques are analyzed and current challenges are described in a very wide investigation. The general process of cold sintering for ceramic matrix composites, including the mixing of ceramic powders with fillers, powder wetting, and sintering. Traditional mixing methods such as ball milling and mechanical stirring can be used to homogeneously disperse fillers onto ceramic. Cold sintering requires a transient liquid-assisted sintering under certain pressure, which then shows similar densification process to that of liquid phase sintering, and thus uniformly wetting is critical in the cold sintering process. The selection of the solvent phase requires suitable fast kinetics of the congruent distribution of the surface ions of the ceramic phase. Determination of specific solvent is difficult, but can be guided through the consideration is solubility data and different diagrams. Kinetics can also be aided with the selection of particle size and particle size distribution of ceramic phase. With multiple component ceramic compositions, binary, ternary, quaternary compounds, etc., we have to be concerned with the relative rates of each chemical constituent, as this can lead to a nanometer. It is also possible to obtain ceramic polymer nanocomposites via cold sintering processes. For example, the zinc oxide ceramic with PTFE polymer nanocomposites is shown on this figure. The starting zinc oxide powders have particle size around 40 nanometers and 50 nanometers, and PTFE have 50 nanometers respectively. After cold sintering using a liquid phase solvent of acetic acid at temperature around 285 centigrade under pressure 300 megapascals, the PTFE phase is homogeneously located at the grain boundaries of the composites, and the nanocomposite is the dense nanocomposite was obtained as shown on the TEM micrograph. Finally, I want to say that it's only a part of up-to-date technology which intensively developed last decades. As you can see, the combination of different technologies and different schedules of consolidation processes it's possible to fabricate materials faster, better, cheaper, and achieve some energy saves and minimizing the ecological pollution. The next lecture will be about how we can apply the synthesis and consolidation methods to obtain ceramics to produce ceramic, nanoceramic parts for in industrial scale. Thank you for your attention.